Exactly 13.8 billion years ago, the clock started. Every particle of matter, every unit of energy, and the fabric of space itself expanded from a single point of infinite density into a rapidly inflating, blindingly hot cloud of energy. This was the Big Bang. For its earliest history, the universe was a superheated, opaque fog. Light couldn't travel because it was constantly crashing into free-floating electrons. It took 380,000 years of expansion for the cosmos to cool enough for those electrons to bind into the first atoms. When they did, the fog lifted, and trapped light burst across the universe. This spherical heat map shows the absolute oldest light we can observe. It's called the cosmic microwave background, or CMB. It serves as a literal infant picture of the universe. By mapping these tiny temperature fluctuations, astrophysicists can identify the specific hills and valleys of primordial matter that would eventually collapse under gravity to form galaxies. The CMB represents the absolute edge of our observable past. We cannot physically look further back. But the highly organized structure we see in this thermal blueprint forces a difficult question. If this is what the universe looked like just after it began, what existed before the clock started? Modern astronomy models assume that large cosmic structures formed uniformly out of that initial explosion, but recent data challenges this. In 2024, researchers discovered a massive ring-shaped cluster of galaxies spanning 1.3 billion light-years across. We call it the Big Ring. It is too massive and too structured to be explained by a single explosion. This forces physicists to consider alternative explanations for the universe's origin. Physicist Sir Roger Penrose proposed a radical alternative known as conformal cyclic cosmology. In Penrose's model, the Big Bang is not a definitive starting line. Instead, it is a transition point. He argues that after an extraordinarily long time, an expanding universe decays into total emptiness. That near-empty state begins to resemble the extreme conditions required to ignite a brand new singularity. Penrose claims that physical evidence of these previous cosmic cycles is already sitting in our data. He points to concentric circular wave patterns buried inside the cosmic microwave background. He interprets these specific rings as the leftover gravitational ripples from the collapse of a universe that existed before our own. The implication is that the universe is an endless cyclical engine of creation and destruction, and out of that infinitely repeating process, highly specific, localized environments began to take shape, including the one we call home. Zooming in from the edge of the cosmos to our own neighborhood, we find a massive, dark cloud of gas and dust drifting through space 4.6 billion years ago. This was the solar nebula. This peaceful cloud was disturbed by a nearby supernova. When a dying star exploded, the resulting shockwaves slammed into our nebula, causing gravitational instability. The dust and gas collapsed inward, spinning into a flat disk. At the exact center, the pressure became so incredibly intense that hydrogen atoms began fusing into helium, igniting our sun. The sun consumed 99.8, yet this intense bombardment delivered the ingredients for life. The incoming asteroids and comets carried ice crystals within their rock. As they smashed into the magma, the water vaporized into the early atmosphere. When the planet finally cooled, the trapped vapor condensed and rained back down to fill the oceans. Having water was a start, but the Earth was far from stable. Roughly 4.5 billion years ago, a second protoplanet, roughly the size of Mars, was locked on a direct collision course with our molten home. Astronomers call this planet Theia. The giant impact hypothesis explains exactly what happened next. Theia slammed into early Earth in a direct collision, completely fusing their heavy iron cores. The immense energy of the impact blasted millions of tons of lighter crust outward, creating a glowing ring around the merged superplanet. Up in orbit, the laws of accretion took over again. That shattered ring of floating magma and rock rapidly coalesced under its own immense gravity to finally form our moon. We know this planetary collision is a physical reality because we went there and checked. When the brave Apollo missions returned from the lunar surface, they brought back dirt and rocks for detailed chemical analysis. Geologists examined these specific lunar basaltic samples and measured their chemical composition. The oxygen isotopes in the moon rocks are nearly identical to the rocks found deep in Earth's mantle. The chemistry proves that the Earth and the moon were once the same body. That catastrophic impact knocked our planet slightly off its axis, giving us a permanent 23.5-degree tilt. That tilt drives the changing seasons that distribute heat across our globe. Meanwhile, the newly formed moon exerted a gravitational pull on our oceans, creating the tides that eventually helped early life transition from water to land. This violent accident is the exact reason our planet can sustain life. Fast forward to the present day. The early solar system's chaos has settled down, leaving us with a balanced environment that allows humans to thrive. But the stability of our oasis masks a difficult reality. We are trapped by the physical scale of the expanding universe. The distances between star systems are so immense that humanity is effectively marooned inside our own solar system, bound by the rigid speed limits of standard physics. Look at the Andromeda Galaxy, our closest cosmic neighbor, sitting 2.5 million light-years away. Traveling in a modern spacecraft at its top speed of 28,000 kilometers per hour, it would take us over 94 billion years to reach it. We routinely use powerful telescopes to locate potentially habitable Earth-like exoplanets deep in the cosmos, but discovering them is useless if we can never physically cross the distance. To leave our galaxy, we must find a way to bypass the fundamental laws of spacetime. Einstein's field equations of general relativity describe exactly how mass and energy warp the fabric of space. Because they define space as something that can be bent, these equations offer the theoretical framework for finding shortcuts through the universe. The most famous of these shortcuts is the Einstein-Rosen bridge, commonly known as a wormhole. By folding three-dimensional space through a higher fourth dimension, a tunnel can connect two unimaginably distant points, cutting a multi-million light-year journey down to a few minutes. A functional tunnel requires a stable exit. Einstein's math suggests that if a black hole creates the crushing gravity needed to open the entrance, the other end requires an opposing force. Physicists call this a white hole, a theoretical object that expels matter outward rather than sucking it in. If tunnels prove too unstable, there is another mathematical solution to faster-than-light travel. The Alcubierre drive envisions a ship that doesn't move through space. Instead, it moves space itself by contracting the space-time curvature directly in front of the vessel and expanding the space behind it, surfing a wave across the cosmos. Humanity is a byproduct of violent cosmic history, and while we are currently restricted to a single star system, the same chaotic mathematical laws that birthed the universe contain the theoretical solutions required to eventually leave it.